Hello, today we're going to have a brief introduction to equilibrium reactions. So equilibrium happens when you have reversible reactions. If you have your reactants and they can be turned into products, but the products can also be turned back into reactants. We usually use a double arrow like that to indicate that the reaction is reversible. Sometimes chemists get lazy and do little half arrows. Either way is fine. Just make sure that you don't do a double-headed arrow, because a double-headed arrow in chemistry is for resonance. So that's something different. Lots of different types of reactions are reversible. They can be chemical reactions or physical processes. So when you're changing state, you can reverse that and go, like if you're melting something from a solid to a liquid, you can then, of course, freeze that liquid back into a solid. So that's a reversible physical process. But you can also have reversible chemical reactions as well. It just depends on the type of reaction. And a good example of an equilibrium reaction could be where you're dissolving an ionic solid. So if you have something like lead-2 chloride, it will dissolve into lead-2 ions and 2 chloride ions. But lead-2 chloride likes to form a solid, so it will very often go in the reverse direction as well and form that solid lead-2 chloride precipitate back again. So that's how you kind of get to reversible reactions. Now, when you have that kind of reversible reaction, eventually the forward reaction and the reverse reaction are going to be happening at the same rate. So that's really important. Forward and reverse are happening at the same rate or same speed. Okay. Once we get to this magic point, okay, we call that equilibrium. And we call it a dynamic equilibrium because the reactions have not stopped. Okay, that's a really common misconception. Reach equilibrium, the reactions have stopped. No. The forward reaction and the reverse reaction are happening at the same speed. So therefore, it looks like nothing is changing. Because you wind up with a constant amount of reactants and products, but the reactions are still happening. Okay, so reactions continue. But you have constant amounts of reactants and products. So those are kind of like the main things that you need to know about a dynamic equilibrium there. Now we talked a little bit about phase changes, but a common example that the College Board likes to use for dynamic equilibrium is when you have vapor in a sealed container. So let's say we have a closed container like this, and you have a liquid in that container. Okay. At the very beginning, when you put that liquid in, there's no gas. But the highest energy particles, the ones that have enough kinetic energy, are going to start to evaporate until it reaches its vapor pressure, until it reaches equilibrium. So the pressure exerted by the particles of a gas above a liquid is called the vapor pressure. And essentially, when it reaches that state of equilibrium, you have particles evaporating from the liquid. At the same rate, you have particles condensing from a gas to a liquid. So if you were to look at the pressure changes here over time, you wouldn't have any pressure to begin with because we're putting it into an empty sealed container. But the pressure would slowly increase as more and more of that liquid evaporates, and then the pressure would kind of level off because you reach that state of equilibrium where the evaporation and condensation is happening at the same rate. Okay, so let's talk about equilibrium concentrations. Remember, when we reach equilibrium, the forward and reverse are happening at the same speed. Reactants and products. So let's say, let's track it on a graph. Right. So let's say amount over time. All right. At the very beginning, if you start with just reactants and you have no products, okay, the forward reaction will start to happen because you have reactants. So the reactants will start to decrease and they will turn into products. All right, and that's going to continue. But once you start having some products, some of those products are going to turn back into reactants. So that the speed will slow down, or I'm sorry, this change in the amount will start to slow down. That's a better way of putting it. The change in amount will slow down because some of the products are now being used up. And so it will start to level out. And the same thing for the reactants. The amount will start to level out. And when you reach a constant amount, that's the time that it reached equilibrium. Now, you could also have a graph that looks just a little different. You could have you're starting with reactants and no products. You could have it where over time, as the reactants are being used up until it reaches equilibrium. But you could also have it so that the products, as they're increasing, they could wind up being more than the reactants. And that's fine. It depends on the particular reaction or process. As long as when you reach constant amounts, that's when it reaches equilibrium. You can also reach equilibrium if you, and your amounts, if you have just products to begin with and you don't have any reactants. You can still reach equilibrium that way. But, you know, as long as it'll level out like that, and when it reaches constant amounts, that's when it reaches equilibrium. Okay, so for this reaction, we have our balanced chemical equation, and it's reversible, and they gave us that there's 1 atm of A and 1 atm of B. We can use pressure or moles for this. Because we have pressure, we know pressure is directly proportional to moles as long as the volume is constant and the temperature is constant, which we assume that it is because they don't give us any of that information. So we can assume that the pressure there, we can treat it just like moles, just like we're counting for the numbers of particles. Now, we want to graph to show the reaction as it proceeds to equilibrium. So on our graph, I have 1 atm of A and B and 0 atm of C and D. Okay. And then it says sketch a graph to show the reaction as it proceeds to equilibrium. Upon reaching equilibrium, there's 0.8 atm of A. So if this is 1, this is like 0.8, okay? So A is going to decrease to 0.8, all right? But look at the coefficients here. There are twice as many B's. So B is used up twice as fast as A. So if you'll notice, we've got 1 atm of A, and then you wind up with 0.8 atm of A. It loses 0.2. 0.2 of it reacts to form C and D. Your 1 atm of B, it will be twice as much. So you'll wind up with 0.6 atm for B, because this is 0.4. So here-ish for B, A, and B. And again, that's because you're using up B twice as fast as A. Now for C and D are formed at the same but reverse rate as A, because it's a one-to-one relationship between A and then C and D. So since A is going down by 0.2, C and D will both increase by 0.2. Like this, C and D. And they'll have the same line there. And so on my graph, equilibrium is reached just about there. Okay, now for this second example, we want to write equilibrium reactions. Freezing, melting of benzene. So that's a physical process, but we've got C6H6 solid. It can melt into C6H6 liquid, but it can also go in the reverse to freeze. And that's it for that one. Dissolution of the weak acid HCN. Okay, dissolution is a fancy way of saying dissolving or dissociating. So we have our HCN aqueous, and when it dissolves, it forms hydrogen ions and cyanide, like that. So it dissolves, and then it can go back together again, especially because it's a weak acid. Only some of it dissolves into ions, and those ions like to come back together. And then for part C, the proton transfer between the weak base HS negative and the weak acid H2PO4 negative. So this is acting as a base, this one's acting as an acid. This is kind of a review from Unit 4 with acid-base reactions and conjugate pairs. And it's saying there's a proton transfer. So the acid is going to transfer one of the hydrogens to the base. So this is an H2S. And the other thing will be HPO4 2-. And so H2S will be the conjugate acid, and HPO4 2- will be the conjugate base.